Okay, so the first thing we're going to do is have a look at some standard integrals that we can now do. A few of them we've met before, but a whole bunch of them are new because we've met lots of new differentiation in year 13. And basically, integration is the inverse of differentiation. So if we know how to differentiate, we can just reverse engineer that to know how to integrate something. So we're going to do that. We're going to have a look at things we can differentiate and therefore make a statement about things we can integrate. And I'll start with what we knew already, what we've done in year 12. If I have a polynomial, y is x to the power n, then we know that differentiating this drops the power down by 1, but also multiplies by the original power. So if I differentiate, I got n lots of x to the n minus 1. And what that tells us is that integrating nx to the n minus 1 with respect to x equals x to the n. It just is the opposite, except for I need to add a plus c to this and to this, because remember, differentiating a constant gives us nothing. So there may be a constant which vanishes when we differentiate. So if I'm integrating, I may have a constant that appears because when I differentiate it would have disappeared. And I don't know, that constant could be anything, but that constant always appears when we're doing these indefinite integrals because it might have been there when we were differentiating. This is a mess though, and I don't really want a mess. What I want is something neat. I'd much rather reorganize this and see what it looks like to integrate x to the power n. And you can see all I've done really here is I've dropped this power by 1, so I really need to drop and increase this power by 1, so I need to increase this power by 1. So this is going to give me x to the n plus 1. And this n has vanished. So what I need to do is, instead of going from here to here, well, this is dividing by n, the new power. So I still need to do that division by the new power, but it will be here. And I still need my plus c, that doesn't change. And hopefully that looks pretty familiar. Okay, integrating a polynomial raises the power and divides by the new power. But we're reverse engineering differentiation. And so it looks like this. Integrating polynomials, straightforward. Raise the power, divide by the new power. Similarly, and very simply, what happens when we differentiate e to the x? Well, dy by dx equals, surprise, surprise, e to the x. Differentiating doesn't do anything. But we mustn't forget we could have had a constant there. So integrating e to the x with respect to x does absolutely nothing except potentially makes a constant appear. Integrating doesn't change it because differentiating doesn't change it. So integrating e to the x, still e to the x. Number 3 is the natural log function. And again, this is one of these standard things that we looked at when we were differentiating back in chapter 9. If I differentiate the natural log of x, I get 1 over x. Okay, standard function, that's just what happens. So if I want to integrate 1 over x with respect to x, what I get is natural log of x plus some constant c. Now it is worth noting, right here we use the modulus sign here for the integration because 1 over x can absolutely be negative, but I can't put a negative into the natural log function. So we use the modulus function as a standard here when we integrate, just because it removes any potential issues with that. So integrating 1 over x, now absolutely possible. Remember that if I come back to our linear one, 1 over x is x to the minus 1. So integrating x to the minus 1 according to this rule would give us x to the x to the 0 divided by 0, which was problematic, right? So we can't use this standard rule for 1 over x. However, because we know how to differentiate natural log, we can now integrate 1 over x. It's the thing that works. We also have our trig functions. So we talked about sine x. If we differentiate sine x, then we get cos x. Easy peasy. So that means if I want to integrate cos x, I get sine x plus that constant. Okay, that's a simple one. In the same way, if I want to differentiate cos x, then dy by dx equals sine x. Except it makes it negative. Okay, so we get negative sine x. Again, that means I could write the integral of negative sine x with respect to x equals nice positive cos x plus some constant. But we'd much rather not have the minus sign in the integral, because we're saying I want to integrate this nice easy function sine x and see what we get. So what we tend to do is we tend to just switch those two around and say, well, that means the same thing as integrating sine x gives us negative cos x. I'm just multiplying everything by -1. Absolutely fine, doesn't make any difference. So that's dealing with sine and cosine. We also looked at how we differentiate tan. Now, this is one of the standard integrals, standard differentials that we can look at, and it just gives us sec squared x. If you want to remind yourselves why that is, it's back in chapter 9, and it's because tan is sine over cos, and we could use the chain rule or the quotient rule to tackle that. But we looked at that and it's sec squared, and therefore if I want to integrate sec squared x, I get tan x. It's just not that big a deal. And those are the three standard trig functions, sine, cos and tan, which we knew how to differentiate, and therefore we can reverse engineer and integrate. But we also looked at the other three trig functions. We also looked at cosec, sec and cot, and we established how to differentiate them. And because we can differentiate them, we can also integrate them. So we just need to remember, if y is cosec x, then dy by dx equals, and again, we worked through this step by step back when we were looking at chapter 9, but now that you know how now you know how it works, you're allowed to just memorize and state that it becomes cosec x cot x. And as a result, the integral of negative cosec x cot x with respect to x equals cosec x plus c. But again, just like the sine, integrating sine, we don't really want this negative in here. We'd rather pull it out and therefore make the answer negative. So what we get is, if you want to integrate cosec x cot x, the answer is negative cosec x. And in the same way, we also know how to integrate, differentiate cot x. So if you differentiate cot x, dy by dx equals negative cosec squared x. And again, therefore, the integral of negative cosec squared x is just cot x plus c. And again, we don't really want that minus sign within our integral. So our standard integral is integrating cosec squared gives us negative cot plus some constant. And the final one is that we can integrate sec x, and if we differentiate, and if we differentiate sec x, we get sec x tan x, and therefore the integral of sec x tan x is sec x plus c. Those are less straightforward to remember, except that all we're really doing is reversing our differentiation. So if you remember that differentiating sec gives you sec x tan x, then you also know what the integration is. Okay, so this is in the textbook, and we've got this summary of these 9 things. The first one was, well, we already knew that from year 12. That's just integrating polynomials. But all of the rest of these are new to year 13. And the reason we know them is because we know how to do the differentiating. There's nothing surprising or complicated here, but there's a whole chunk of stuff that you need to hold in your head, but really it's just the differentiation you need to hold in your head, which hopefully you've already done a bit of practice on. I also want to point out that this little snippet down here is from the formula book in the differentiation section, and you can see that it tells us differentiating tan gives us sec squared, integrating sec squared gives us tan. It tells us that differentiating sec gives us sec tan, so integrating sec tan gives us sec, and similarly we've got cot and cosec giving us these two. So whilst I have just said there's lots to memorize, actually the only new things you need to memorize are these ones, because the other 4, 6 through 9, are in the formula book, but they're in the differentiation section. You just need to remember that integration is the reverse. So if they're written in the differentiation section, you can still use that when you're integrating.